Okay, so hi, my name is Rosalind. I'm going to present a piece of work on that we did on trying to estimate the age-dependent susceptibility and probability of showing symptoms by age, led by Nick Davies at London School. So what we noticed very early on, and everybody noticed, is that there was a lack of children in the observed cases, and so we, as everyone, were wondering why. And so what we decided to do was test the fit of models where the model had either varying susceptibility to infection by age or a varying clinical fraction. So this is the probability of showing symptoms severe enough that you'd be picked up, that you'd seek care for them, basically, or whether none of these things were happening, and the difference we were seeing was only due to contact pattern differences. Because very early on we saw this, the epidemic in Wuhan occurred during the school holidays, and indeed the initial spillover event was into older people. So we thought, perhaps just that early spillover into adults followed by school closure in a population with relatively fewer children. Maybe it's just, that there's a lack of kids. And then finally, whether it's both varying susceptibility and varying clinical fraction. And so we explored this using an age stratified transmission model in 5-year age bands. And we fitted this to a range of data from Wuhan initially, and then to the early phase of epidemics in a few countries that were themselves doing different interventions, especially with regard to school closure, which is the most important for looking at this. So I haven't had any time to make into a nice presentation. So these are just the figures from the paper. So that's why they're busy, but I'll talk you through them. So the model is up here. You have a subclinical route and a clinical route up here, where there's some transmission before the onset of clinical symptoms, and that's there. And in the base case, we assume that subclinical infections are 50% as infectious as clinical infections, but I'll show a little bit that it's not tremendously sensitive to that, but that is the base assumption. And what you can see in this figure, this is just fitted to Wuhan. We have our model with age varying, there's always age varying contact patterns, which come from a contact survey in Shenzhen, I think in 2017. And age varying susceptibility in orange, age varying probability of showing clinical symptoms in blue, and neither in red. And so what you can see here, we took the model, and the black dots are the epidemic in Wuhan, confirmed cases. And then we have here 1, 2, 3, 4 snapshots of the age distribution, and that's shown in the wireframe, that are drawn from different papers published around the same time. And so we fitted to the incidence, that's all age incidence, and we fitted to these age distributions for each of these models, model variants. And what you can, and then also, like I mentioned before, the schools were closed in Wuhan, but also there's this Lunar New Year holiday followed by the lockdown. So in the model, we had a contact multiplier, which increased or decreased the contacts during the holiday period and during the lockdown. And we also closed schools at the correct time. So we have, underneath this is a varying mixing matrix that closes schools, increases for holidays, decreases for lockdowns. And that means that we also estimated the reproduction number for each of these models, which is what you can see here for model 1, model 2, model 3. Oops, sorry. And then it goes up during this pre-holiday period and down during lockdown. Okay, so what you can see is that the model 3, the red one, where it's just contact patterns, it doesn't fit the observed age distribution at any point. So we think that there's more going on with that, which seems maybe it seems kind of obvious now, but like 2 months ago, it didn't seem quite so obvious. And then we have model 1 and model 2 with our varying susceptibility and clinical fraction, which do a much better job at fitting the observed age distribution at each of these time points. But if you have only age-varying susceptibility and you have the same amount of asymptomatics or subclinical infections at all ages, then that implies rather a lot of subclinical infections in older adults. That's these old orange bars here. We're saying that 20% of cases in 20% of the subclinical infections you would expect to see in the 70 plus, which, as we're learning more things about this, about COVID, it seems very unlikely that you would have a big chunk of your subclinicals in your oldest age groups, where we know now we're seeing more severe infections. And so what we did also then is fit this fourth model variant that had both age-varying susceptibility and age-varying clinical fraction. And that fit, according to DIC, the best. But I personally also just find that M1 is not convincing as a concept because of this excess of subclinicals. So then we took forward this idea that you could have both susceptibility and clinical fraction varying by age, and fitted that to data from a range of countries. So what you can see here in the blue is the age distribution of confirmed cases for a number of regions in China. Oops, sorry. In kind of these orangey colors for a range of regions of Italy. And we also fitted to data from Japan, Singapore, South Korea, and Ontario in Canada. And because more information was coming out from other types of studies about the susceptibility or the probability of showing symptoms of children, for instance, these contact tracing studies by B and Zhang from 2 regions of China. Then there's this study, Lavezzo, which comes from Vaud in Italy. Tan, this is a study of from Vietnam of in an isolation center. This big study from Iceland, giving some information on the probability of kids being infected, and a really big study from Italy on the distribution of symptoms by age. So we included these into the likelihood estimation for this fitting. And what we fit here is the stationary distribution of the next generation matrix for these areas using local contact matrices and closing the schools if indeed the schools were closed in these areas. And then up here you can see the country by country fit and the overall consensus fit here for the clinical fraction in the solid line and the susceptibility to infection in the dashed line. And you can see that there's quite a marked lower susceptibility in 0 to 20s before it rapidly rises to something which is essentially flat, which is quite interesting to me. This one makes sense that as people get older, they're less likely to have a subclinical or, if you like, asymptomatic infection, except in the very youngest, which is kind of a classic pattern that you see. And as kind of a validation, we fitted different regions that were not included. We fitted the time series for some different regions, and then asked the model to reproduce if it could reproduce the age distribution seen. So it's fitted to the time series, but validated on the age distribution. And the gray one is when you use the consensus consensus values above, and the colored one is when you use the local one. And you can see here that South Korea has this funny 20 to 30 peak, which we think is that big church outbreak that they had, making things a little unusual. And you can see again in Italy, much higher than expected older people. So the key point then for why does this matter is it has quite a big impact on the on interventions aimed at children, interventions in general, and especially those aimed at children. So here we're comparing our COVID fits of susceptibility to infection, severity, so that's the clinical fraction, and the similar thing that we would, this is just a schematic for flu, where kids are more susceptible and older people show more symptoms. And to demonstrate the effect of this, we took 3 regions with very different demographics. So this is Milan, which has a median age population of 43, Birmingham, 30, and Bulawayo is in Zimbabwe, which has a triangular age distribution. And you can see there, though, the relative for COVID and for flu, you get very different age distribution of, well, both total number of people infected and the age groups that you expect to see those cases in. For me, the biggest difference was that surprised me was just how different it was for these between Milan and Birmingham, which I don't think of as very different. Okay, so that's in an unmitigated epidemic. And then up here, what you can see is you have schools open in the solid line and closed in the dash. And these 3 panels, 1, 2, 3, are the infectiousness of subclinical infections. So 0, they don't transmit at all. 1, they're as infectious as clinical infections. But you can see here that although there is a difference, and that's what the panels down here are showing, it's not that big of a difference, really. And this is because the kids are not really, they're not very susceptible at all. So when they do become infected, it does make a difference, but that is unusual. And so this is a comparison to flu, where we know that school closure, or we think that school closure has a really big effect. And the model closes schools for 3 months, which is why you basically just push the epidemic off the end, except in Bulawayo, which has a higher number of children, and you can see you diminish the epidemic. Okay, and so that's the effect of school closure. But then we also use the model to say, because there's a lot of concern that for what is going to happen globally, because if we think about the epidemic, what we normally would expect for a flu-like epidemic is that places with a large number of children would have a much more intense epidemic, and the reproduction number may be higher, and you would expect things to be a lot worse, which is why I think there is a great deal of concern towards what would happen, say, in Africa, amongst other reasons, obviously. And so what we've done here is take this is the capital city of 150 countries using synthetic matrices from Prem et al. They're colored according to the I think it's World Bank region. And then you can see the total unmitigated clinical attack rate and the peak of that unmitigated attack rate. And then over here is the subclinicals. So if you want the total attack rate, you add together the clinical and the subclinical. So these are high attack rates. But what you can see here is that the reproduction number is not that different across in different places, the projected reproduction number, because the children are not that susceptible to infection. We'll just ignore D and E for now. Okay, so there's also, because there is a lot of concern for the epidemic in Africa, so we were using this clinical fraction estimated only in high and upper middle income countries. So we did a sensitivity analysis. The red is what we estimated in the paper, and then we just kind of made this clinical fraction a little bit more, a little bit higher at all ages to kind of make the epidemic a little bit worse, to give projections of, so that to make sure that we weren't kind of underestimating what could happen. And that's what you see here, where you have the high and upper middle clinical attack rate projections and the low and middle, lower, middle, and low projections. Okay, I think I'll stop there in the interest of time.
Thank you very much.